All right, this is lesson 3.8, which is determining if a point is a solution. So there are two different situations. There's like solutions graphically and there are solutions algebraically, which we haven't really talked about this one yet. Graphically, a solution is a point that's on the line of solutions. So looking here, for example, the y-intercept is a point on the line of solutions. So that's why it's a solution. This point here is also a solution. Any of the points on the line is a solution to the graph because it's on the line. Algebraically, a solution is a point, still x comma y, that makes the equation true. So when I talk about an equation being true, that means when you substitute it into x and y, you get 4 equals 4 or 6 equals 6. So that's how we know algebraically if it's a solution. So moving forward, the question is the coordinate a solution? Before we really begin, let's write this equation. I've wrote the skeleton here so that I can write the y-intercept and the slope. So the y-intercept, here's the y-axis, the y-intercept is 2. Then I need to count my slope. So I picked 2 points, as you see here. I'm going to count the rise from the leftmost point, which is up 1, 2, 3, 4 units. So rise, up 4, and then run, which is right, 1, 2, 3 units. Right, 3 units. So the equation of this line is y equals 4/3 x plus 2. So if a point is a solution, okay, we're going to see what that looks like algebraically, and then it makes the equation true. 3 equals 3, 2 equals 2. 2 points that we can use. I'm going to choose some difficult points for my demonstration, or I should say more difficult points, like that one there, and those two. So the point -3, -2 is a solution because it's on the line, and the point 3, 1, 2, 3, 4, 5, 6 is also a solution because it's on the line. So what does that mean algebraically? Separate this, make a little bit of room. That means in the equation y equals, 4/3 x plus 2, if I substitute in the point -3, -2, it should make it true. So I'm going to go ahead and label my points x and y, or maybe I'll color code them because I prefer that. And I'm going to substitute -3 in for x. Then I'm going to substitute -2 in for y and simplify. 4 divided by 3 times -3, because that's x, plus 2 equals -2. Put -3 over 1, multiply straight across. -12 divided by 3. -12 divided by 3 is -4. -4 plus 2 is -2. Since -2 equals -2, this point is a solution. I'll do the same thing for 3, 6 very quickly. Y equals 4/3 x plus 2 at the point 3, 6. So I substitute 3 in for x and 6 in for y. Simplify. Put 3 over 1. 4 times 3 is 12. 12 divided by 3 is 4. 4 plus 2 is 6. Since 6 equals 6, this is a solution. It makes the equation true. To contrast that, let's talk about points that are not solutions. So points that are not solutions are anything that are not on the line. So for example, this point over here, this point's not on the line, so it's not a solution. That point is 2, 3, 4, 5, 6, 1. And really, any point that's not on the line is not a solution. So this random point over here, which is negative 1, 2, 3, 4, 5, 6, 7, 8, negative 8, 0. That's also not a solution. So I'm going to test those 2 points to show algebraically what that means. Substitute negative 6 into the equation. So at 6, 1. I'm going to label my points, x and y, so that I can substitute them in. 6 in for x, 1 in for y. Put 6 over 1. 4 times 6 is 24. 3 times 1 is 3. 24 divided by 3 is 8. 8 plus 2 is 10. Does 1 equal 10? Heck no. Not a solution. That's why it's not a solution, because when you substitute it in, it's not a true equation. You get 1 equals 10. Doesn't make sense. Try the same thing for negative 8.